So hi everyone, welcome to today's webinar. We are very happy to have with us today Kenza Benkirane. She will be, sorry, one second. There is some echo. Hi, okay.
Yeah, go ahead, Amy. It's okay.
So welcome. Okay. Just check if I have this. I have YouTube open somewhere. Yes. Oh yeah. I think it's fixed now. So welcome everyone. Thank you for joining us today. For today's webinar, we have with us Kenza Benkirane. She will be presenting her latest work on machine translation hallucination detection for low and high resource languages using large language models. She will share some insights from her latest publication in EMNLP 2024, where she evaluates sentence-level hallucination detection using large language models across 16 language directions spanning diverse scripts and resources. And Kenza Benkirane is a biomedical engineer with a background in data science and strategy consulting. She specialized in artificial intelligence at University College London, where she developed expertise in large language models, culminating in a publication at MNLP 2024 on machine translation hallucination detection, which is the topic of today's webinar. She works currently as an AI lead at Vivanti, a medtech startup, and Kenza is also actively engaged in promoting multilingual and fair natural language processing, reflecting her commitment to equitable and inclusive AI development. The talk will last for approximately 30 minutes, followed by a 10-minute Q&A. If you have any question during the talk, please feel free to ask them in the chat, and we will be sure to address them at the end of the presentation. And thank you for being with us today. And please, Kenza, the floor is yours.
Thank you so much, Iman and MoroccoAI, for organizing this. I'm going to share my screen. Can you see it?
Yes, we can see it.
Sorry?
Yes.
Yeah, or good. Yeah, we can see it.
Amazing. So I'm going to share with you my work on machine translation hallucination detection, just as Iman introduced. This was done last year around April with my UCL colleagues, but also Mila, McGill, and Meta colleagues. So this was a group work, so mostly done with UCL people, and Laura Gangas, which is my co-author. So before I deep dive into any methodology or technical explanation, I would like us to deep dive into a use case. Let's say that you're from the UK and you're traveling to Nigeria, where one of the main languages is Yoruba. You come across a sentence in Yoruba, which is the following. In English, this means always you should reserve a seat with an airline company via a telephone. You're trying to translate this sentence to English, but this is the Spanish. To Spanish, I forgot the example. And this is the translation that you get. You always remain seated with the airline in the glass. So as you can see, the translation is absolutely not correct, but most of all, it has a hallucination. The part in the glass is semantically not linked to the input sentence. So here, if you happen to speak both Yoruba and Spanish, you would be able to spot a hallucination. But if you're translating blindly, you can have problem translating for low resource languages. So the problem is that machine translation can have and generate hallucination, particularly for low resource languages, which are languages way less available on the broad internet. And this can be quite dangerous, not only if you're translating that you should reserve your seat online, but if you're translating healthcare information or law information, this can be actually dangerous. And the actual methods that exist today in NLP are mostly towards high resource languages, particularly English, but do not show good results for low resource languages. So here we had as a research objective to really evaluate hallucination detection, but emphasizing on low resource languages. And for this, we decided to use the latest NLP methods, being large language models and embedding spaces. We decided to use this as a binary classification task. So hallucination or no hallucination, I will give more details about this. So let's say that back to our example of these two sentences, now we know it's a hallucination, but wouldn't it be amazing if we had some specific methods such as embeddings and large language models to correctly classify if that's a hallucination or not? So this was the scope of our study and the context. More precisely, we used the Halloumi dataset, which is from Meta, that is using the Blazer model, and also provides a very wide data set with 18 languages directions, meaning we have both from English to the language and from the language to English. And we also have non-English centric translations. So this data set has high resource languages being English, Arabic, German, Russian, Spanish, and Chinese. And for low resource languages, we have two Indian languages being Kashmiri and Manipuri, and Yoruba, as I mentioned, which is from Nigeria. And finally, for non-English centric, we have Spanish Yoruba translation in both directions. So we use this data set. We use German as a validation set, which is quite often done in machine translation tasks. We had 301 sentences for both directions, and we used the other 16 directions for the testing. So the baseline is the same model as the Halloumi paper was using, which was the state of the art back then. It's a model that is based on multiple translation sentences, so it's dedicated to translation. It was also made available, the embedding space linked to this model, which is Sonar, was also made available by Meta, and we will present this more precisely later. So why binary classification? We must underline that originally the dataset was based on severity ranking. So we had 4 ranking per sentence, which was no hallucinations, small hallucination, partial, and full. But looking more deeply at the dataset, we realized that there is a very high class imbalance, particularly across low resource languages, which makes sense as hallucinations are still a rare phenomenon, but it was not really relevant. For example, from English to Russian, we had only 1 sentence with small hallucination and 2 sentences for both partial and full. So seeing these figures, and for example, seeing that from English to Kashmiri, we had 19% of full hallucination and only 60% no hallucination. Seeing all these results and imbalances, we decided to binarize the datasets. So make the small, partial, and full hallucination just hallucination label, and to still evaluate on severity ranking as an ablation study that you can find in the appendix of the paper. We made another choice, which was to not use the classical machine learning metrics. We used here the Mathieu correlation coefficient. This was very important because, as I just mentioned, hallucinations are rare, meaning that true negative are just as important as true positive, as much as false negative and false positives are important. So we had a choice between using multiple metrics or trying to find one metric that is more easily interpretable. It has values between -1 and +1, and it also evaluates the model performance from the confusion matrix scores. So we decided that the MCC score was way more robust given our project. So in terms of methodology, as I mentioned, we evaluated with both large language models and embedding spaces. For the large language models, we used 3 prompts and 2 chain of thought variations. All of them were with zero-shot learning. We realized that few-shot learning was actually confusing the LLMs. This was based on a few papers and also a pre-study we did with only Yoruba English. So we decided to focus only on zero-shot. And we used a wide range of large language models, 8. So GPT models, Command R models from Cohere. We used Sonnet 3.5 was not there yet, I believe, Opus, and also Llama 3 and Mistral 8.22b. So for the prompting, we had a system and user prompt. The system prompt was based on the same architecture all the time, but with variations, as I mentioned. So first, a task description, a definition of hallucination, and a few variations which were specific language instructions, meaning that we would mention which language the source and translation text would be, so that the LLM could identify the language. This was not available in all prompts. And also we used in some of the prompts some chain of thought. We also should mention that the Halloumi dataset that we used was based on human annotation, which makes it a great dataset. And it also gave in the paper all the instructions that were given to humans to classify the hallucinations. So we used these same human instructions for the LLM, of course, with some variations, but this was our inspiration, with also some papers, mostly GFL, to build the prompt. So this was for the system prompt design. For the user prompt design, we didn't use much variation, only gave the source text, the translated text, and then asked if there was a hallucination. We used a open label, which was hallucination or no hallucination. There was a pre-study that was actually a module coursework from UCL, where we tried multiple labels with binary 0, 1, hallucination, no hallucination, but also some other random labels just to binarize the output. And we found that, which was actually confirmed by more serious papers, that having a more explicit label allowed the LLM to understand better the tasks, which made sense. This is why I'll use this user prompt across all the system prompts. And finally, in terms of evaluation, just as for embeddings, we used German as a validation set. And for each model, each LLM, we selected the best prompt with the highest MCC score. And then we ran inference for that model with that prompt with all the other 16 languages pairs. Sorry, it's 8 languages, but 16 languages pairs. So this was a methodology for large language models. For embedding spaces, it was way more minimal. First, we encoded the source and translation sentences and calculated their embeddings. Generated their embeddings. Then we calculated cosine similarity for each sentence pair. And based on this similarity, we calculated with the validation set, the German validation set, the optimal threshold to maximize the F1 score. I think you should see the animation. So here we evaluate This is a classical machine learning method to find a threshold for which there is a maximum F1 score. Here, the little complexity is that the more similar the two sentences are, the less hallucination there is. So we just inverse the cosine similarity, but this is a detail. The method remains the same. And after that, we use this threshold for binary classification with a test set for 4 embedding spaces. Sonar is the first embedding space that I mentioned, developed by Meta, which is based on translation sentences, and it's the embedding space linked to Blazor, which is the state of the art. And then we used GPT text embedding 3 large, which is the biggest embedding space with I think a dimension of 3042, if I remember correctly. Then we use Cohere Embed v3 and Mistral Embed, which are smaller but also linked to the large language models that we used. In terms of results, maybe what everyone may be looking for. We had very interesting results. In gray, the first model that you can see is the previous state of the art. And in the following 4 models are actually the embedding spaces with Sonar, GPT, Cohere, Mistral, and finally all the LLMs that we used. So the first comment is that LLM can outperform the previous state of the art without being explicitly trained on translation specifically, which is very interesting. We can also see that it's outperforming Blazor from a lot. I think it's 16 MCC points. Also, it's MCC, so it's between -1 and 1, hence the low results compared to if it was F1 score. What we can also see here is that embedding spaces are actually very competitive for such a low resource method. It's way less expensive than large language models. It doesn't require much prompting. It was a very simple machine learning method, but we can see that from high resource languages to English, embedding spaces are actually outperforming Blazors and also outperforming a lot of our large language models. Also, each large language model is tested here with its best prompt. So it's it's quite impressive that embedding spaces can have such results. Another quite obvious result is that we can see that high resource languages, again, have way better results than low resource languages. Our target was to have better results with low resource languages, which we actually did. For example, with Spanish to Yoruba, we can see that Claude models are really doing well, way better than Blazor, which was explicitly trained for this. From Yoruba to Spanish, we can see that also GPT-4o is doing way better than it has been previously. So we can see some trends here that large language models can actually have better results than these specifically trained models, as we mentioned. Another very interesting point is that we can see that embedding spaces are not doing well when it's low resource languages, and models with reported better reasoning capabilities do have better results. So one question that we had, one open question, is that maybe at some point when there is no specific knowledge of that language in their data set, if Yoruba is not in their data set, maybe here the reasoning capabilities are more important so that they can find patterns in the data. This is one of the interpretations that we had for these results. But most interestingly here, we can have large language models and even less expensive methods such as embeddings to evaluate hallucination. after translation, which is the biggest finding. So as a conclusion and future work, the performances factors are the resource level, high resource and low resource languages, meaning that there is not one model that fits all the resource levels, not one model that fits all the translation direction, not one model that can be used for all the script types. All situations show that each model had their strengths and weaknesses. So there is lots of work that is still needs to be done. And yes, maybe one big finding actually is that we found that for non-Latin scripts, for example, with Arabic and Chinese, we had very good embedding results, better sometimes than large language models. There's way more details in the tables in the paper, which is quite interesting, showing that maybe for other scripts, the embedding spaces and the cosine similarity may be stronger than the large language model evaluating such languages. We also saw from the results that some directions are doing way better. Most of the time, when it's to English, it's doing way better because the large language models obviously are better in English. So translation to English are better to large language models are better to identify hallucinations when it's translating to English. And finally, obviously, we saw that Latin scripts were easier, as I just mentioned, but with non-Latin scripts, we can use embeddings. So we have still lots of challenges. We have good results, but we still have low performances for low resource languages. Here we only had 3 low resource languages, 2 of them from the same country. And from what I know from the latest of my researches, I'm not sure there is any other data set for hallucination detection, neither with severity ranking. This needs lots of work, especially for low resource languages, especially when we want high quality data set. This means that we need more engagement from local population to be able to annotate data set with low resource languages. Also here we had a very high dataset imbalance, which affects the evaluation. As I mentioned before, if Manipuri has more hallucination and if some models are better with a true negative, for example, then it would help the performances for these specific cases, which shows that our evaluation may not be quite fair across languages. Also, we only had one translation that was without English, which is Yoruba Spanish, which I'm not sure is quite used today between Spain and Nigeria. For example, we could think of French to Derija. This would be very interesting to see as a translation. And finally, here we did binary detection to make sure that our results were robust mathematically. But the severity ranking is quite interesting. So we still did the study as an ablation study, but we would need more fine-grained evaluation, not only about the severity. Here, the severity was about the number of words hallucinated, but also about how semantically far the hallucination can be. This could be a very good open research question. Yeah, I think that's it. Thank you very much for your attention. Lots of other things to say about it. Please check the paper and feel free to ask a question, any question.
Thank you so much. Thank you so much, Kenza, for the talk, and congratulations on the paper, on having a paper in a top conference. That's a great topic to work on. So you mentioned, just start with the questions. You mentioned the efforts that we have to do in order to improve the resources and the data for Darija, for example, dialect and low resource languages at large. in your opinion, what would be, or what should we focus on in terms to, or prioritize in order to, in terms of working on low resource languages to improve these kind of models and have less hallucinations and have robust models even for translation?
I think data is obviously the biggest need, or it's called low resource languages because of this lack of data. We can see lots of information on the internet with high resource languages, with English, French, etc. But once we look for data sets in Derija, that's very hard to find. We most of the time find modern standard Arabic, MSA, or other Middle Eastern Arabic, but for example, for Darija, it's really hard to find that. Having more data and having more local people speaking the language, annotate the data sets, would allow us to have way more power, maybe to fine tune, to make sure that the language can actually understand cultural subtleties. I think there's lots of work being done with lots of community. I worked with Masahan for this paper, which is based on African languages, but I also know that MoroccoAI, Atlas AI, there's lots of work on Darija particularly. But yeah, this is a problem across all lower source communities.
Yeah, definitely. So this leads me to the next question. Did you have Darija as low resource language in your experiments in this work?
No, this was with Manipuri from India, Kashmiri from India, and Yoruba from Nigeria. So no Darija, unfortunately.
Okay. So maybe we need more work on Darija to have more robust and other models, including for hallucination detection. We have other questions. We have a question from Benkirane. How did your team implement few-shot learning? Did you put the examples in the prompt directly or fine-tune the model with a couple of examples?
So we actually use zero-shot learning, but we did a pre-study with few-shot learning, and there it was directly implemented in the prompts. Yeah, we didn't do any fine-tuning because there weren't that much data. For each language, we had more or less 150 sentences. This was not enough for fine-tuning.
Yeah. And there is another question on prompting techniques. Were there any other prompting techniques like self-reflections, self-reflection used in this work?
So we thought about it, but unfortunately we couldn't do it. Also, this paper was done in March, April last year. So at that time, we didn't have yet that many papers on self-reflection. We did think about auto-CUT back then, which I think is quite close. But no, we didn't have time to implement it. But we put it in our future work.
Yeah. Okay, we have, I think the people here at the audience are very interested by the topic and the paper. We have so many questions today. We have another question from Omar. We know that Claude Sonnet is, at least for now, one of the best closed source LLMs for Darija. What are some of the key insights that we can easily translate from your work on Arabic to Moroccan Darija? And how can we use this insight to reduce hallucinations in models like English Darija, Tarjuman machine translation model? I think you hovered on Moroccan Darija. Yeah, but maybe just a comparison between Claude.
So there's two questions, right? One about Claude,
Yeah.
and how can we use the findings of the paper for Darija, correct?
Yeah, exactly. For the English Darija translation.
Okay. So for Cloud, unfortunately here it was Cloud Sonnet 3 and Opus also 3, there's no other. We didn't use 3.5, and yes, indeed 3.5 is really, really good for translation and for lots of tasks. In terms of translation from English to Darija, I would say that it's we would expect it to have the same performances as this group for hallucination detection. We also found that there was a correlation with multilingual benchmarks results and our hallucination detection results here. So I would expect Sonnet 3 obviously to be higher than Sonnet 3.5, sorry, obviously to be higher than Sonnet 3. Yeah, actually that's a very good experiment to try. I'm sure that here it's maybe as good as Blazor. And in terms of how can we use these results for translating, I mean, I think that there's lots to learn. I'm not sure that if the Arabic results can be transferred to Darija. Also, I know there's lots of paper evaluating how LLMs can be better or not than machine translation models. To be quite honest, I'm not really sure how it can do. We only have to try because Darija is it's quite an interesting NLP problem because if you think of Darija written in Arabic script, or if you think of Darija written in Latin script with numbers, if you think about more or less subtle ways to speak Darija, I think there's a lot of tasks to try, lots of subtleties to try. But yeah, from the latest paper that I've seen about translating with LLMs shows that they do have better results than some machine translation models, but specifically translated specific machine translation models can have more subtleties and more accuracies on some tasks. So yeah, I don't know, maybe at some point we'll have something in between. Yeah, lots of open questions and research questions.
Exactly. Yeah. I think that extends to like for Tamazight in Morocco or in North Africa, with different depending on the cultural differences between the regions, and there's a lot of work there to be done.
Yes, definitely. Embedding is also very interesting, I think.
Yeah, exactly. We have another question. When you compared Blazor, did you binarize the predictions from those 4 categories to yes and no to binary classification?
Yes, we did the binarization before. Yeah, we did the binarization before, but there's also an ablation study where we compared Blazor with severity ranking to LLMs with severity ranking, and obviously Blazor with binary classification compared to LLMs with binary classification.
Yeah, I think there is another question on the same topic, asking how did you pass from embedding to binary classification? Were there in a neural network through in between? Or?
This I think it's this method that, if I understand the question correctly.
Yeah, exactly. So Simo is asking about how did you go from embeddings to binary classification to binarize the output?
Sure. So we had the input sentence and the output sentence, the translation, and we generated the embeddings of each sentence, calculated the similarity between the 2 sentences. Then we calculated the optimal threshold to have the maximum F1 score. I think you can see this as a video. It was, yes, the threshold for which there is the less mistakes on each side of the thresholds. Mistakes being costing the most to the F1 score in this scenario. Yeah, and then we use this threshold, meaning that for the test set, we also calculate cosine similarity. When it was above the threshold, it was no hallucination, and below the threshold, a hallucination.
And in terms of robustness of the metrics or the similarity, do you think there are some other methods that can be used to better will be more robust to capture the differences or to capture the hallucination or differences between the different sentences?
So here, I think this one is quite good because of what is in red in the formula, that it takes into consideration everything, but it also makes the metric more dispersed, sorry, between -1 and 1. So it means that 1 point is way more, it's way more, it has more information for each point than, for example, the F1 score. I'm not sure. I mean, we evaluated lots of metrics. I don't want to say this is the best. Maybe I don't know all of them. And that's possible that there's a better one, but from our evaluation, this was the best one.
There is another question about the interpretability. Did you address the interpretation of these detection methods in order to, for example, to check what are the elements or what went wrong in the, or what made the hallucinations pop up in the translation?
So the translation was already in the data set. So we use these methods to identify the hallucination post-translation. The translation was done with an LLB from Meta, so everything is from Meta in this data set. We didn't think about interpretation. This is actually one of the evaluation that we think is still a challenge, to really evaluate which token provoked the hallucination in the translation, but from the machine translation model perspective from an LLB. So this was a post-analysis, so there we didn't go this far.
Yeah. I think we with good works we end up with more open questions than the ones that we started with, so it's all good. So thank you so much, Kenza, Benkirane, for the insight, for the talk, and for all the information that you shared with us today. I will stop the streaming on YouTube, and then we'll move to the breakout rooms. For the attendees, stay with us. You can go to the breakout rooms where you can meet with Kenza and ask